Today's lesson will be on acids and bases. We'll start by mainly defining what's an acid, what's a base, using both the Arrhenius and Bronsted-Lowry theories. Looking into all the important things to look out for in identifying and describing what is an acid and what is a base. Then we'll look into simulations that will help us explore various examples of common acids and bases microscopically. Look into their pH values and so on. Lastly, we'll have a detailed discussion on the pH scale, the pH equation, and once again providing examples at different levels of representation that will help you develop a good conceptual understanding of acids and bases and the pH scale. To access all the simulations that I'll be using in this lesson, just simply go to phet.colorado.edu, then chemistry, then for this first simulation, click on the acid-base solutions, then the play button. Next, you'll be given two options, the introduction and my solutions options. We'll be using both of these great simulations. PhET simulations are really amazing and incredibly useful in promoting inquiry-based teaching and learning, and they provide a solid alternative to the traditional laboratory-based inquiry education. So after clicking on the introduction, you'll be taken straight into the acid-base solutions introduction simulation. In this simulation, we are given a microscopic representation of the following reaction, which is based on the autoionization of water. At this point, you just have to know that in every water molecule, we can get a single hydronium ion, the H3O plus ion, and a single hydroxyl ion, the OH minus ion. You will see how both of these two ions will be very important in determining acids and bases. And for now, you just have to know that water has an equal amount of both of these ions, the hydronium ion and the hydroxyl ion. If you look at these diagrams used, it will be very useful to note how, with these two water molecules, one hydrogen and two oxygen atoms are bonded together. One of these water molecules is simply going to donate one of its hydrogen ions to the other water molecule, so that it then forms the H3O plus ion, which is a positive hydronium ion. Because one of these water molecules has essentially gained the hydrogen atom, hence formed the H3O plus instead of the H2O water molecule. And the one water molecule that donated its hydrogen ion is now left as just OH minus, basically one hydrogen less since it donated it. On the right of the page here, we have our solutions. Clicking here will show a strong acid, a weak acid, a strong base, and a weak base. Next we have views. Leave it on molecules, and then you can check this box to show your solvents. I'll leave it unchecked. Then we can click here to show a bar graph representing the water, molecules, the hydronium ions, and the hydroxyl ions. Then we can click here to hide the contents of our container. At the bottom here, you have various tools, the pH meter, a sort of litmus paper, and this awesome tool showing a light bulb connected to two electrodes, which basically work on the basis that they will conduct electricity between them, hence light up this bulb if there are ions in the solution. And I have already mentioned earlier that in this water solution, we will have one hydronium ion and one hydroxyl ion. And because of this, water will conduct electricity and switch on this light bulb. You will see later how the number of these ions in other solutions will influence the current flowing through the circuit, and the bulb will shine and glow brighter. Now at this point, I'll begin with defining an acid. For this, we use two theories, the Arrhenius theory and the Bronsted-Lowry theory. These two theories can be used interchangeably. According to the Arrhenius theory, an acid is any substance that can ionize in water to form hydronium H3O plus ions. And the Bronsted-Lowry theory defines an acid as any substance that can donate a hydrogen ion, therefore any substance that can be a proton donor. To illustrate all of this, looking at this simulation, we have a molecular representation of an acid ionizing in water to form hydronium ions and some N ions. At the top right of this page, now we have our solution. Firstly, the acid or base options. I leave it on acid. Then we can adjust the concentration of the solution. Then select the strength of the solution. Here you can select weak or strong, or also move the slider towards either side to make the solution weaker or stronger. Looking at this simulation, we have a molecular representation of an acid ionizing in water to form hydronium ions and some anions. The acid is represented here as HA and is shown here in the form of these dark gray molecules. Then we have our water, which is our solvent, and remember, we have unchecked the solvent option. Clicking on this will show the solvent, and as you can see, the solvent is this light gray molecule, and we know that it's there. I will once again uncheck this option so as to hopefully draw your attention to the ionization of this acid and the products formed thereto. Looking at this closely, you can see how this acid HA is donating its hydrogen ion, this small circle here, to the water H2O molecule. This forms the red H3O plus hydronium ions and the blue anions. That is now left without the donated hydrogen. Now this here illustrates both theories mentioned earlier. Firstly, it confirms the Arrhenius theory in that we can clearly see how the acid HA, which is a hypothetical acid and can be used to represent any acid, will be ionizing in water, which simply means it will be forming ions, and as a result of that ionization, or as a product of this reaction, we see how these red hydronium ions are being formed. And for this to occur, we see how this acid HA must give away or donate this hydrogen ion. Now moving on to defining a base. Firstly, let's toggle to base. According to the Arrhenius theory, a base is a substance that can dissociate in water to produce hydroxyl OH- ions. And the Bronsted-Lowry theory, on the other hand, defines a base as a substance that can accept hydrogen ions and therefore can be referred to as a proton acceptor. Now looking into this simulation showing a base B in dark gray reacted with water, our solvent, we see how this base B will produce the blue hydroxyl OH- ions and these yellow cations. For this to happen, note how the water molecule H2O is donating its hydrogen ion, and the base B then accepts this hydrogen ion to form the BH plus ion. And the water molecule is now left as the OH hydroxyl- ion, thus confirming both theories once again. Next, we will define, explain, and illustrate the differences between weak and strong acids, then look into weak and strong bases. We have discussed how an acid is any substance that can ionize in water to form and produce hydronium ions. However, it is easy to imagine that not all acids will produce an equal amount of hydronium ions when ionizing in water per unit of volume. Thus, the concept of a weak or strong acid. A weak acid can be defined as a substance that can only partially ionize in water to produce a low concentration of hydronium ions. And a strong acid, on the other hand, can be defined as a substance that can completely ionize in water to produce a high concentration of hydronium ions. So looking at this simulation, note how the number of hydronium ions changes as I toggle between weak and strong, and also how the amount of HA reacted also differs. With weak acids, we see how there will be much fewer hydronium ions produced, and with the strong acids, there is a much greater amount of hydronium ions produced per unit of volume. Also do note how with the weak acid, not all of the acid is ionizing or partaking in the reaction, and most of it is actually being left unreacted or without ionization at the end of the reaction. However, with the strong acids, we see how the acid has completely reacted and ionized to produce these hydronium ions, which are thus much more compared to the hydronium ions formed in the weak acids. And of course, as complete ionization occurs, there will be a much higher concentration of these blue anions, while for the weak acids, there's a much lower concentration of these blue anions. And now, let's look into the differences between weak and strong bases. A weak base is a substance that can only partially dissociate in water to produce a low concentration of hydroxyl OH- ions. And a strong base, on the other hand, is a substance that can dissociate completely in water to produce a high concentration of hydroxyl OH- ions. Now, looking into the simulation, we see how once again the amount of hydroxyl ions produced by a weak base is much less compared to the amount of hydroxyl ions produced by a strong base. And also, we see how with the weak base, it only partially dissociates, hence most of it is left unreacted and as is. While for the strong base, you see how it has completely dissociated, hence it is no longer present in the container. Now, moving back to the introduction simulation. Once again, this reaction shows how in water, we have an equal amount of the hydronium ions and the hydroxyl ions. This makes water somewhat of a special case, and I will explain what I mean by that a bit later on in this lesson. Once again, looking at the strong acid, we see how there is a high concentration of the hydronium ions produced when it completely ionizes in water. And looking at the weak acids, there is a much lower concentration of the hydronium ions produced, and the acid only partially ionizes. Strong bases will produce high concentrations of hydroxyl ions, and a weak base will produce a much lower concentration of the hydroxyl ions, as it only partially dissociates in water. Now, let's come back to the second tool. The brightness of this bulb will vary depending on the type of solution it is placed in. Once again, this is because the number of ions produced in each of these solutions is not the same. The higher the number of the ions produced, the brighter the bulb will glow. And the lower the number of the ions produced, the dimmer the bulb glows. It is interesting to observe, therefore, how the bulb shines the brightest when the circuit is placed in both a strong acid and a strong base. Once again, this is because of the high amounts of hydronium ions in the case of strong acid, or the high amount of the hydroxyl ions in the case of strong bases that will be produced in each case. However, it shines dimmer when placed in both a weak acid and a weak base. Once again, this is because of the lower concentration of the hydronium and hydroxyl ions produced in both cases respectively. And of course, it makes perfect sense how water will only barely light up the bulb since there is such a low concentration of both the hydroxyl and hydronium ions, as you can see. Next, we'll look at common examples of acids and bases and the pH scale. For this, we'll go back to our PhET chemistry simulations, click on this pH scale simulation, then play. With this pH scale, you have three options: the macro, micro, and my solution simulations. We will start with this micro simulation. On this simulation, we have various examples of acids and bases. Given here are the battery acid, blood, chicken soup, coffee, drain cleaner, hand soap, milk, orange juice, soda pop, spit, vomit, and water. We'll be using the pH to help us investigate these acids and bases, and also through all this get to understand what the pH scale is and how it works, and how to calculate the pH value of any solution. The pH simply refers to per hydrogen ion concentration in a solution. And on this my solution simulation, we can see how the higher the hydrogen ion or hydronium ion concentration in a solution, the lower the pH value of that solution. Conversely, the lower the concentration of the hydronium ion concentration, the higher the pH value of that solution. The pH scale starts at 0 for the strongest imaginable acid and ends at 14 for the strongest imaginable base. Please note, like in the example of water that I showed you earlier, most solutions have both the hydrogen or hydronium ions and also the hydroxyl ions. So you can think of the pH scale as a tool that just continuously compares the concentration of the hydrogen or hydronium ions compared to the concentration of the hydroxyl ions present in a solution, such that when the H3O plus hydronium ions are equal to the hydroxyl ions, like in the example of water, then the pH will be equals to 7. And when the concentration of the hydronium ions is higher than the concentration of the hydroxyl ions, the pH will be in the acidic range, which ranges from 0 to 6.9. And of course, when the hydroxyl ions concentration is greater than the concentration of the hydronium ions, then the pH will be in the alkaline or basic range, which ranges from 7.1 to 14. Back to the micro simulation. So here you can see that once again with water, for example, we see that the pH value is equal to 7. Once again, this is because the number of the hydronium H3O plus ions is equal to the number of the hydroxyl OH minus ions in the solution, as you can see with this molecule count. We can see that the number of the hydronium molecules is equal to the number of the hydroxyl molecules, both being equal to 3.01 times 10 to the power of 16. And on this logarithmic scale, we see that the concentration of the H3O plus ions is equal to the concentration of the hydroxyl OH minus ions, both being 1 times 10 to the power of minus 7. Remember that with the water ionization formula, Kw is equal to the concentration of the hydronium ions multiplied by the concentration of the hydroxyl ions, which is equals to 1 times 10 to the power of minus 14. Back to the acid-base solutions. When I select a battery acid, we see that the pH is equal to 1. This indicates that battery acids are examples of strong acids. Please note how adding water increases the number, hence the concentration of the hydroxyl ions present in this solution, which then increases the pH value. Also note how in this reaction, water is a base or alkaline solution since it produces and increases the hydroxyl ion concentration, and it's accepting the hydrogen ions donated by this strong acid, which is what forms the high hydronium ion concentration compared to this much lower concentration of the hydroxyl ions. On the other hand of the pH scale would be something like a drain cleaner, for example. Firstly, as you can see, its pH value is 13. This time the number and concentration of the hydroxyl ions in the solution is much higher than the number and concentration of the hydronium ions. Thus the pH value of this solution is 13. Now note how when we add water in this solution, this time this increases the number and concentration of the hydronium ions in the solution, thus lowering the pH value of the solution. The two examples I've just explored, the first including battery acid and water, then this one with a drain cleaner and water. Remember how in the first reaction, water was acting as a base, and in this reaction, it is now clearly acting as an acid. As you can see, it leads to the production of more hydronium ions, and this lowers the pH value. So this means water can act as both an acid and a base. Thus, water is an example of an ampholyte. Ampholites are substances that can act as both acids or bases. The pH can be calculated through the equation pH is equals to minus the log of the concentration of hydronium ions. For example, with this battery acid, the pH will be equal to minus the log of the hydronium ion concentration, and therefore the pH will be equal to minus the log of 1 times 10 to the minus the power of minus 1. Which will be equals to a pH value of 1. And this drain cleaner, the pH will be equal to minus the log of 1 times 10 to the minus 13, which will be equals to a pH value of 13.